Hi guys, welcome back. Today I bring to you all a very interesting project done by me and my teammate Sahil. Here we have King County House Pricing Dataset. Our objective is to predict the price of the house based on various parameters. Our primary motive is to understand the dataset. It is a good practice to first spend a lot of time analyzing the columns of the dataset. In this dataset, we have 21 columns, namely ID, price, square feet for living, and so on. After viewing the data, we came to our initial hypothesis that price of the house is dependent on area, year built, grade, number of bedrooms and bathrooms. To confirm our hypothesis, we need to perform exploratory data analysis on the dataset. Firstly, we have to check for any missing values in the dataset. Luckily, in our dataset, we had no missing values. Next, we check for how many numerical and categorical variables are present in the dataset. Numerical variables are further categorized into discrete and continuous. Then we plotted histogram for continuous variables to check for skewness. The results were astonishing. We observed that the variables like price, square feet living above were skewed. Then we plotted a bar plot to study the relationship between discrete variable and price. We observed that the relationship between grade and price is exponential and they have a positive correlation. We also plotted a graph of year built versus price and found out that the newer the house is, the greater is its price. Next, we were curious to see the relationship between year renovated and price. Now, if the house was recently renovated, its price was high. From the EDA process, we infer that the initial hypothesis and assumptions made by us were incorrect, and the price of the house depends on various factors other than those taken in the consideration during the hypothesis. Model fitting. We were very curious to see how linear regression model responds to our initial hypothesis. Here we developed three models with target variable as price and the independent variables were the first variable we took was square feet living, and we observed that we got a R square of 0.49 and an RMSE score of 268686.24. Then the next model we took the independent variables as square feet living and grade. Here we observe that we got the R squared value of 0.53 and RMSE score as 258217.71. Later, for the third model, we took four independent variables. As you can see from the table, as we are increasing the number of independent variables, we are getting a better R squared value. Now, further, we think that we can improve this model by applying feature engineering techniques like scaling, log transformation, and data encoding. Feature engineering. Feature engineering is useful to improve the performance of a machine learning algorithm. The few common feature engineering techniques are imputation, one hot encoding, feature hashing, log transformations. Here in our dataset, we have done log transformation as when we plotted a histogram for continuous variables, we found skewness. To remove this skewness, we take log transformation of those continuous variables. But here we should remember the log transform should always be taken for non-negative and non-zero columns. If we take a log transform of a negative or a zero column, it's high chance that we get a NaN value. After feature engineering, our next step is feature scaling. Feature scaling normalizes the range of all the independent variables. In this particular dataset, we have many features which have different units. Hence, it is necessary we do feature scaling to apply particular machine learning algorithm. Here, we tried two types of feature scaling. One was standard scaler and the other was min-max scaler. After getting the results from both of those, we found that min-max scaler performs better with our model because it scales all the values between zeros and 1. But guys, here we have to remember that we need to perform feature engineering as well as feature scaling for both the datasets, which is our training dataset and our test dataset. Now, the next part will be explained by my friend Sahil Gupta as to what happens to the model after feature engineering.
Thank you, Manisha. So, as we have done feature engineering on our training and it has data, we try to fit the above models post feature engineering to see if the performance of the model has improved after feature engineering. We fit linear regression models on the training data and compute the R square and the RMSE score by doing a tenfold cross validation on the training data. So here you can see that after feature engineering, as the number of predictors are increasing, there is a slight improvement in the performance of the model. Here also, we take into consideration the initial hypothesis and the assumptions for the model. So now, finally, we proceed for a linear regression model and find the R square and the RMSE score. We perform a linear regression on featured data and test the model on the featured test data to get the R square and the RMSE score. Here, we consider all the numerical variables in the dataset after feature engineering as a set of predictors and price as the target. We drop zip code, ID, and date from the predictors as ID and date are categorical and zip code is a dummy variable. So from the table, you can see that after performing a tenfold cross validation on the training data, we get a R-square score of 0.77. We fit the model to the test data and we can see that from the test data, we get a R-square score of 0.76. So we can see that the performance of the model has significantly increased as we have increased the number of predictors. So this model can be used for predicting the price of the houses. Further, we try to see that if some other models can also be used for prediction of the price. So we try to fit a decision tree on unfeatured data. Here also we take into consideration the initial hypothesis and the assumptions and try to fit a decision tree regression model on the trained data and compute the R squared and the RMSE values by doing a tenfold cross validation. So from the table, you have seen that we have taken the initial assumptions that we have done for the previous models. And you can see that as the numbers of predictors are increasing, there is a slight increase in the R squared score. Further, we try fitting the decision tree on the featured data. Here also we take into consideration the initial hypothesis and the assumptions and try to fit decision tree regression models on the trained data and compute the R-square and RMSE by doing a tenfold cross validation. So here also we have taken the same set of predictors as in the previous models and the price as the target. So we can observe that post feature engineering and as we are increasing the number of predictors, there is a slight improvement in the performance of the model. So finally, we try to fit a decision tree regression model on our featured data and compute the R square and the RMSE scores. So we fit a decision tree regression model on the featured test data and the training data to get the R square and the RMSE scores. Here also we consider all the numerical variables in the data set, post feature engineering as the set of predictors and price as the target. We drop zip code, ID, and the date from the predictors as the ID and date are categorical variables and zip code is a dummy variable. For decision tree tuning, we perform a hyperparameter tuning to get the best fit model. For this, we vary the depth of the decision tree from the values 1 to 20 with a step size of 1 and calculate the R square value for each depth. And finally, we take the depth in for which the R square is maximum, that is depth equal to 10. So after doing a decision tree regression, we do a first we do a tenfold cross validation of the training data and get the R squared value as 0.82. Then we fit the model to the test data and from the test data, we get the R square as 0.82, which are equal. So we can say that this model is a fit model for our prediction of the price of the houses. Finally, we perform a comparison between the two models. So from the tables, as you can see, the linear regression gives us a R square of 0.76 on the test data and decision tree gives us a R square of 0.82. Similarly, the RMSE scores for decision tree model are better than the linear regression model. So we can conclude that the decision tree model with all the numerical variables as the predictors except ID, date, and zip code and having a maximum depth of 10 is the best fit model for the prediction of house prices. So in this way, we have tried to fit two models to predict the house prices in KC house price prediction model. Thank you.